Okay, so let's try this one. I'm going to show you this one to kind of show you how conjugate beam can start to break down. It will work, but it'll be a little more challenging to deal with. So the first thing I'm going to do is we're going to try to find the slope at A and the displacement at the midpoint. I'm going to use conjugate beam. I know we could solve this problem, and we have using direct integration, but this will be like a little kind of a compare and a contrast. The concentrated equivalent force for the whole structure is WL, and I think, not divided by L, WL. And I think you can probably see, without too much discussion, that the reaction is going to be WL over 2 on the left side and WL over 2 on the right hand side. So we'll kind of cut through that a little bit. So let's go ahead and divide or draw a template, and let's draw the shear force and bending moment diagram for this. First we'll start off with the shear diagram. So we're going to start off with a shear of what? Looks like WL over 2, and that's a positive shear. And I should end with WL over 2, and that's a negative shear. So the change in shear is the area in the load curve, which you can see is WL. The load is down, so it's negative, so WL over 2 minus WL gets you negative WL over 2. So that matches. And also the shape of the curve would be given by the loading. The loading is constant and negative, so we have a constant negative slope. So I'd start at WL over 2 and end at negative WL over 2. That didn't come out perfect, but it should be very, very close to the center of the beam. You remember from our previous work, we can find that exact value, x1, right? I know that that value is, when I project it up, would be this area would have to give me the change in shear, which is negative WL over 2, which is half the distance. So I am going through that pretty quickly, but I think you could find very quick, without much trouble, that that's L over 2. So now what does my moment diagram look like? We're going to start off with a moment at the pin of 0, and I better end with a moment at the roller here of also 0. So the change in moment over the first part of this L over 2 should be this area under the diagram, which should be W squared over 8. Right? 1/2 base L over 2 times height WL over 2. So I should get WL squared over 8. And what is the shape of the curve? Well, the shape of the moment diagram is given by the shear. So the shear is going to start off at a positive value and end at a value of 0. So I'm going to get a nice parabolic section there. Over the second section, it's going to start off with a slope of 0 and end with a slope that's negative. And the value of the slopes are the same on each side, they're just different signs. So I may not have drawn it that way, but that should be a nice parabolic segment with an axis right here at the center. You see that? So that's not so bad yet. We'll see. So now I need to write or draw my conjugate beam and apply this as load. So what might conjugate beam for this look like? What's the pin at A become in the conjugate space? A pin. What about the roller? So really the conjugate beam, the geometry looks exactly the same. Well, that's nice. So I'll draw the beam. pin, roller. And now, like we've been doing for a while, I'm going to just transfer this moment diagram as load. And then I'm going to determine what direction that load is. This is all positive moments, so the load is up or down? Up. So now I've got a parabolic load that looks like that. And we know it's symmetric, L over 2, L over 2. And I also know that this peak value here is W L squared over 8 EI. Okay? So the problem first asks you is, what is the slope at A? Now the slope at A in the real beam is what in the conjugate beam? The shear. So I really need to find what's the positive shear at A. I know positive shear at B would look like this. So how do I find the shear at A in this free body diagram?
The area under the triangle.
Well, I would, some moments about B, right? So to do that, what am I going to do with this thing? I need to find a concentrated equivalent force. What is the concentrated equivalent force? What's the area under a parabolic section?
2/3 base.
That's right. So the force will be 2/3 the base, which is L, times the height, which is WL squared over 8 EI, which is what? That's WL cubed over 12 EI? That look right? And since I'm going to sum moments about B, you can see my moment arm is L over 2. So that really doesn't look too bad. So if I sum moments about B, make sure it's in equilibrium, my force, equivalent force about B is creating what kind of moment? Positive or negative? Negative, right? So I got minus WL cubed over 12 EI. Moment arm is L over 2. Then I've got the shear force also creating negative moment times a moment arm of L. So what is the shear at A? It looks like it's negative. It looks like it's going to be WL cubed over 24 EI. That look okay?
Yeah.
So it just so happens in the front of your book, I'll slide this in here. There's our beam, and there's the slope. I know it's hard to see, but it says WL cubed over 24 EI. And the plus minus means it's negative on the left side and positive on the right. And we're doing the left side, so we got a negative. So that's good. So really, looking at the amount of work we did, that's not that bad, is it? Probably the thing that's scary, though, is this. And the fact that you would need to know the area of a parabolic or spandrel section. But still, it depends on the problem, so it's not so bad. Now, to finish the problem off, what's the displacement? Oh, time's up and class is over. So I'll stop here, and maybe I'll finish this off for you on Tuesday. But on Tuesday, we'll start some new topics too.